So today our topic is talking about friction clutches. So we're going to discuss the friction clutches. So in this case, we'll be focusing on the torque capacity and the power transmitted. Where possible, you even find that at times it doesn't just end there. You can also find questions that are asking for you to calculate the amount of heat that is being dissipated by the same clutch. Okay, now let's, as usual, pick up the introduction. So we have so many types of clutches. We have clutches that are used for transmitting motion or power between shafts using fluid. Others are also electromagnetic clutches, but in this case, the ones we're dealing with today are purely based on friction. So even the material that is selected for this is one that is able to conduct away the heat at a faster rate and maintain the efficiency of the mechanism. So when here, what we normally do is that we want to transmit motion from one rotating member to the other one stationed without, first of all, stopping the rotating member. We want that motion to continue and be stepped. So what comes in between, that is a mechanism. Our mechanism is a clutch. In this case, we are particularly referring to one which relies on friction, hence a friction clutch. So first, we talk about the torque capacity. The torque capacity refers to the torque that a particular clutch is able to transmit. And if you look at the mechanism of the clutch, it will have an inner radius and an outer radius. We're going to be calling the inner radius as R1, the outer radius as R2. And if you consider a small elemental area whose thickness is dr, then the area will be, the length is 2 pi r. So meaning that your area, which is length multiplied by the width, gives you what we've written here. So if you're looking for the force exerted on this small area, you multiply pressure by the area. So you just introduce pressure by the same expression for area we talked about. But then we can still rearrange this where we can say friction force acting on the elemental area. This is just a force, but if we talk about the friction force, then we introduce now the coefficient of friction to join the party or to join the whole group. So that's why now you have mu, then the z, the whole of this, just as we had it earlier. What about the torque? If you're looking for the torque, it means you multiply force, the friction force, by the radius. So the whole of this expression multiplied by the radius, meaning that everything will remain the same, but this r will end up having power 2. So the torque acting on the elemental area therefore becomes mu p 2 pi r squared dr. This is in the torque acting on the elemental area. So then we've multiplied. In other words, what we're saying is that this is our inner radius, this is our outer radius. But the area we're talking about here is, as we shall see, more like a mean radius. It's a radius at the point where we're doing the analysis. That's why there's no need for us to put either 1 or 2. So what is the elemental area? What is that area of an element? We're talking about 1, like that, center. Then we pick a small area around this same clutch, whose thickness, I'll just do that. You can finish there. This is the thickness dr. To get the circumference, we say 2 pi r. So 2 pi r multiplied by dr is the one that is giving us the area of this element we're analyzing. So then the force is pressure times area. So pressure times this expression for area. Then at the same time, torque is force by radius. So we have force multiplied by the radius. Meaning whatever we have here, everything that we're having, multiplied by the radius. But then if we're talking about the friction force, then it becomes, we introduce coefficient of friction there. So this is now the full version you have here. But when you introduce R to all that, it means this radius here carries, it becomes radius of R raised to power 2. Now what do we do? Why don't we go right ahead and integrate this expression? So integrating this expression between the limits R2 and R1 means that we're now getting not just the torque on the elemental area, but the whole clutch, the whole plate clutch. Now here we need to talk about the conditions. We can assume either uniform pressure or uniform wear. So in this case, we are going to consider that this clutch is being subjected to uniform pressure. The other way of talking about this is that this clutch is new. It's completely new. It's not worn out. For a worn out clutch, that's where we use the condition of uniform wear. So P is constant. Then we start the integration. In our integration, you'll notice already that we have R2 and R1. And when you integrate this, it becomes R raised to power 3. So what you have now is the bigger one, R2 cubed minus R1 cubed. Then the other constants also follow along. 2 is still there. But when you integrate 2, it becomes something like this. R raised to power 2 plus 1. Again, everything divided by the same 2 plus 1. Now we already know 2 plus 1 is actually 3. So that's why here we have a 3. Then the power also, we also have the 3. Then we substitute for R2 and also for R1. So R2 cubed minus R1 cubed. The rest of this remains like that. This is our torque capacity. And you may decide to leave it at that. If you've been given the pressure, life is that simple. But if you've not been given the pressure, but instead you've been given the total spring force, W, then the expression becomes mu W R2 cubed minus R1 cubed over R2 squared minus R1 squared. Now here we're introducing small letter n to represent the number of pairs of surfaces in contact. If it's a single plate clutch, it has 2 sides, and each side will have its own pair of surfaces in contact, and then that will give you the total torque capacity that you're dealing with without leaving out any hanging problems. Let's talk about uniform wear. For uniform wear, we talk about the product pressure times radius, PR, being equal to constant. Now here, we said it's either we say it's uniform wear, or we're going to say we are dealing with a new clutch. Sorry, not new. For uniform wear, not new, but old. This is an old clutch. Uniform pressure, that's why we have a new one. But this one, a worn out clutch, it's an old. or worn out clutch. When you see this condition, they're basically talking about the condition of uniform wear, where we consider PR to be equal to constant K. Let's take it from where we were when we said torque T is equal to 2 pi mu K. Then under the root, integral R to R1. So what we had was actually R squared. But in this case, it's not going to be squared because P and R are taken away by this K, which is a constant. So PR is constant and hence they represent K. We can't even integrate them. They're no longer part of the variable. Then we can now integrate this one. When we integrate this one, you'll notice we have, this is R. We integrate R raised to power 1. So it will be 1 plus 1 over the same 1 plus 1. This is one of my favorite problems. 1 plus 1 will always be 2, unless we're dealing with Boolean algebra or something else. So this is the 2, and on top they are squared. So this is squared. But this 2 which we have here, we'll end up cancelling with that 2 because we have 2 right there. And at the bottom, from this integration, we end up with a 2. Hence, this 2 and that 2, they cancel. So hence, you end up with just this expression. So we have pi mu K, R2 squared minus R1 squared. Where we're saying that K is a constant represented by PR, product of pressure and the radius. Suppose this has been provided. Well, in case you've been given, if you have been given the load W, then things change. You end up with this. Actually, what happens now is that this disappears. Then you end up now expanding what is in there. So you have mu W, R2 plus R1, or R1 plus R2 over 2, then small letter n. Where small letter n, like we had said, basically representing the number of pairs of surfaces in contact. So if it's a single plate clutch, you have 2, double, 4. If there are 3, you end up with 6 and so forth. But always listen, try to pay attention to the phrasing of a question, phrasing of a situation, or phrasing of a mechanism, because you may find that as you are counting, trying to come up with small letter n, you've also been given a condition that there are also some of the surfaces that are inactive. If that is the case, then you're also going to be careful to give the correct number. So what is this? This is the average radius. That being the case, then we can simplify this. It becomes torque is equal to mu W R small letter n. This is in terms of when you've been given the total spring force. If you haven't, then you know where to go up there. Let's do the application. So we've been given that there's a single plate clutch, inner radius and outer radii are 200 millimeters and 350 millimeters respectively. The coefficient of friction for the material of the clutch is 0.25, required to transmit power at 800 RPM. If the total spring force is 1 kilonewton, determine the torque capacity and the power, assuming uniform wear, uniform pressure. So we're calculating two things. We're calculating where is it? Oh, it's here. So we need the torque capacity as well as the power under uniform wear, an old clutch, or uniform pressure. This is a new clutch. All right. So as per tradition, we cannot just go into the working. Just find the data. First thing we've been given is the radius. The inner radius is 0.2. because it was 200 millimeters. So when we convert the 200 millimeters to meters, we simply divide it by 1,000 and we have 0.2 meters. Then we proceed to the outer radius, the external radius. The outer one is 350 millimeters. So when you divide 350 millimeters by 1,000, you end up with 0.35. That now takes us to the next part, which is the average radius R, where we're saying 0.2 plus 0.1, 0.35 over 2. We get the average from there, and we get 0.275. Coefficient of friction for the material of the clutch is 0.25. The total spring force is 1 kilonewton, which is 1,000 newtons. And this engine is running at 800 revolutions per minute. This is a single plate clutch, so we expect it to have two surfaces, meaning each of the surfaces of this plate, when in operation, when it is transmitting the torque and power motion, is going to have two pairs of surfaces on each side. So our small letter n is 2. So from here, condition number 1 was asking us to find the torque capacity and the power, assuming that this clutch is old, assuming that this clutch is worn out. So what we have is T is mu WRN. So with that, we substitute. Our coefficient is 0.25. Our spring force is 1,000. Our mean radius, we just calculated it as 0.275. Small letter n is 2. Once you enter that in your calculator, you should be able to find 137.5 Newton meters. 137.5 Newton meters. Next, we also have the power. The power is 2 pi nt over 60. So 2 pi nt, everything being divided by 60. So here's my 2 pi. The n is 800 revolutions per minute. Torque is what we just found up there. It's 137.5. Then divide all of them by 60. So what we get is a power of 11,519.173. So assuming uniform wear, assuming this is an old clutch, a worn out clutch, then these are the parameters we found. The torque is 137.5, and the power that it is going to transmit is 11,519.173. Part B is the case where we're going to assume that this is going to transmit uniform pressure, meaning it's a new clutch. Let's see. So for a new clutch, the torque capacity, when we've been given the load, the total spring force, this is the formula we use. We say 2/3 mu WR2 cubed minus R1 cubed over R2 squared minus R1 squared, then small letter n. This is for uniform pressure. Let's proceed then. 2/3, okay. Then mu is 0.25. W is 1,000. R2 is 0.35. So 0.35 cubed minus R1 is 0.2, also cubed, over the same 0.35, but this time squared, minus 0.2, also squared. Everything remains in the brackets, then we multiply by 2. That's for the 2 is coming from this. Our torque capacity is 140.909. This is a new clutch. The old one was transmitting 137, but this is new. So that's why it's transmitting 140. Let's now try to see, what about the power? Power, we said, is 2 pi nt over 60. So 2 pi times 800 times the t, which is 140.909 over 60. So 11,804.772. That is our power being transmitted for a new clutch. Now, it doesn't matter whether we've been required to find the parameter of the radius, or is it the spring force. You basically use the same expressions that we've discussed here and transpose what you're looking for. Is it the number of surfaces that you're looking for? Is it the coefficient of friction? You make it a subject and you get your answer. And you get your answer. So here, see how you do that in this exercise. And feel free to let me know when you need to reach out.